problem this week is to try to find an expansion for this expression, a plus b to the n. That's what section 5 of Unit 2 is all about, a section called the Binomial Theorem. And if you've made a start on that section, then you'll have already seen expansions in the special cases when n equals 2, that's a plus b squared, and n equals 3, a plus b cubed. What we're going to do in this program is to look at the special case when n is equal to 6, a plus b to the 6th. And we're going to try to find that expansion by a method which is going to be useful when we come to consider the general formula. And believe it or not, we'll find that that method is intimately connected with another problem, and that's finding routes through these streets in the city of Edinburgh. But first of all, here's John Mason to talk about the special case, a plus b to the 6th.
This is the expansion for a plus b to the 6th. But if you want to find it for yourself, you've got to start by being sure that you know what this means. Well, something raised to the power 6 means 6 copies multiplied together. Let's look at that a little more closely and see how a plus b to the 6th can be broken down. A plus b to the 6th can be written in a rather different way, like this. We can split off one copy of a plus b and multiply it by a plus b to the 5th. Now treat a plus b to the 5th as a lump and split up the other bracket. We can write it as a times lump plus b times lump, and gives us the 6th power in terms of the 5th, the 5th power in terms of the 4th, the 4th in terms of the cube, and the cube in terms of the square. We know how to work out the square, so change direction and build up the 4th power, like this. It's a times the cube plus b times the cube. Obviously, you could continue like this and work out a plus b to the 6th, but you can see that already it's getting quite complicated. In fact, there's much more going on here than a lot of laborious multiplication, and that's why we're going into it in detail. So let's go back to the simplest case of a plus b squared. Now, whenever possible, I like to be able to get a picture of what's going on. And for squares, that's easy. Use a square. This square has sides a plus b by a plus b. It's made up of 4 pieces, each one of which is formed by choosing either an a or a b in this direction and either an a or a b in this direction. For example, a by a, b by a by b, and b by b, which adds up to a total of a squared plus 2ab plus b squared. Well, that's the square. How about the cube? The name gives it away. Use a cube and compute volumes. Here is such a cube. It has sides a plus b, and a plus b. And as you can see, it comes apart into little pieces. Each one is formed by choosing either a or b in the 3 directions. This one is b by a. Let's store that over here. Now there's another piece at the back here which is exactly the same shape. So I'll put it in the same place. And on the top here, there's another one like those, but I'm not sure where it is at the moment. Here's a bigger piece, which is a by b by a by b by a. Let's see, there's the little b cubed. We'll get rid of that one immediately. Now there are 2 more big ones here. The same volume. Here's the missing one. And finally, a cubed, which all added up gives me a cubed plus 3a squared b plus 3ab squared plus b cubed. Well, how about a plus b to the 6th? All I have to do is ask for a 6-dimensional version of a cube. That's a little difficult geometrically. However, we can use exactly the same principle of choosing, but concentrate now on the symbols. So let's go back to the square. When we're calculating a plus b times a plus b, we choose one symbol from each bracket and multiply them together. Choosing a from each bracket gives AA. You could choose a from the first and b from the second. You could choose b from the first and a from the second. And finally, you could choose b from each bracket. Adding all these together gives the answer, which we usually write like this. You can use the same idea for the cube. Choose a from each bracket. Well, there are lots of other choices. And finally, the b cubed. You end up with 8 terms, which, collected together, look familiar. So that's the square and the cube, and now for a plus b to the 6th. The symbolic manipulation is exactly the same, as you can see on this board. My job is to choose one letter from each of these brackets, 6 of them all told. Of course, I have to do this in all possible ways. But that's just one choice. As you can see, I've got one b, and the rest are a's, which contributes an a to the 5th b. However, this b could have come from any one of those 6 brackets, and so ended up in any one of those 6 slots. Consequently, there are 6 contributions of a to the 5th b. And that means that the coefficient should be 6 in the expansion. But there are other terms in the expansion. How about them? Well, each one is made up of a collection of letters, 6 letters, and a number in front. That coefficient is the number of ways of choosing that number of b's from 6 brackets. For example, a to the 6th is formed by choosing no b's, that is, all a's. And of course, there's only one way to make this choice, so the coefficient is 1. Now, suppose I ask you to compute the coefficient for a to the 4th b squared. Well, you have to be able to compute for me the number of ways of choosing 2 b's from 6. That's not quite as easy as the ones I've been doing. But this choosing idea is very important, and it crops up all over the place, even when you're walking in the streets of Edinburgh.
The reason we've come to Edinburgh is because this part of the city, around Princes Street, is built in a very regular way. You see, the streets form a rectangular grid pattern. Some of them run east-west, and other streets run south-north. So you see, these 2 streets form the corner of a rectangle. And on the diagonally opposite corner is one of the famous landmarks of Edinburgh, the Scott Monument. Supposing I wanted to walk from here to the monument, one way would be to walk south towards Princes Street and then turn east, walking directly to the monument. Well, that's one possibility, but of course there are other ways. I could have started by going east and then taken a south turn sometime later. What I want to do is to set a little mathematical puzzle, and that's to find out just how many routes there are from here to the monument. So let's start off by seeing what happens if I take an east turn first. Well, I've reached the corner, and I've got to make my first choice, whether to go east or whether to go south. I think we might as well go south. Well, we've reached another junction now, and I've got to make another choice. Obviously, I don't want to choose to go up that way west or north. That's taking me back to where I came from. I want to get to the monument over there. So, again, my choices are south or east. For a change, let's this time choose to go east. Of course, once you're in the middle of the grid of streets, you lose all sense of the route you're taking. But it's all right, just as long as you always make sure to turn either east or south at each of the junctions until you can see the monument. Well, there's another junction. Let's go east again. Oh, this time, let's try south. Now east again. Well, I've got here and I'm at the top of the monument, and from here you can see part of the streets along which we've come. There's Prince's Street that I walked down, and these are the streets running east-west. You can see those on this little map I've drawn. This is where we are now on the monument, and this is Prince's Street. These are the other east-west streets, and this is where we started. And the route we took to get here was, remember, we first started going east, and then we went south, and then east again. Then we continued going east and took another south turning, and finally we turned east again to get to the monument. There are all sorts of other routes you could have taken, but can you see that whatever route you choose, you've got to take 2 choices south and 4 choices east, whichever one you choose to get from there to there.
So here's the link with the binomial theorem, choosing 2 from 6. Just as for each route you have a corresponding choice of 2 souths from 6 direction, so in the coefficients you get a contribution of a to the 4th b squared for each choice of 2 b's from 6 brackets. So choosing 2 from 6 is common to both problems. We're back where we started, but the root problem gives us a way of picturing the choosing process. And from that, it makes it very easy to see what's going on.
When I got here before, I came down Prince's Street along there. But I could equally well have been walking eastwards down this street. But whatever route I took, to get here, I must have come along one of those 2 streets. And I must have come past one of the 2 junctions, the last junctions on Prince's Street and on this street. Now, if I knew the number of different routes to each of those junctions, then I could easily work out the number of different routes to this monument. I just add those 2 numbers. And that's the key to the problem, because that argument will apply equally well to any of the junctions inside that grid of streets. Well, I'm at one of the junctions now, right in the middle of this rectangular grid, and it doesn't matter which junction it is, because I know that to get here, wherever I am, I must have come down a road like that or a road like that. I must have been walking in a southerly direction or an easterly direction. And that's the whole crux of the problem. To work out the number of ways of getting here, all I need to know is the number of ways of getting to that junction and the number of ways of getting to that junction, and just add the 2. Once we've got that idea, we can start filling in some numbers on the grid. Well, this is where we started, and this is where we want to get to. The numbers along these borders are easy to fill in, because if we look at this one, for example, the only way of getting to that junction is along there. So that number is one route. Similarly, to get to there, I must have come along there, so it's 1 along there. To get to here, I can only come down that route, and similarly all the way down this border. All these numbers are 1. That's very easy. Well, the border shots are quite easy. You reach difficulty, first of all, when you consider the first one of the grid points. Now, to get to that point, I can only have come down that road or that road. So the number of ways of getting there is just the sum of these two numbers, and that's 2. What about this one? To get there, I must have come down here or here. So I add those two, and that gives me 3. This one is the sum of those two, so that's 3 again. This number here, 3 and 3, is 6. This number, 3 and 1, is 4. This number down here, to get to this point, I can only have come along there or there. The total number of ways then is the total number to get there plus the total number to get there, and that's 5. And this number is just 6, add 4 is 10. Now we can write in our answer. To get to the monument just here, I must have come along that road or that road. 10 and 5 is 15, and that's the total number of ways of getting to the monument from our starting place.
So there are 15 ways of choosing 2 souths in 6 directions. And the corresponding thing in the expansion is the fact that there are 15 ways of choosing 2 b's from 6 brackets. So the coefficient of a to the 4th b squared must be 15. And how do we work that out? We do that by associating with this point the term a to the 4th b squared. But there are other terms. To work them out, go to a bigger grid. Every time you go east, you get an A. To get 6 A's, keep going. To get 5 A's and 1 B, go south from a to the 5th. To get more B's, go further south. Until you've got all 6 B's. The coefficients that we want are given by the root problems to these diagonal points. Now we're all set to work out the pattern. We start at the beginning with a 1, which says there's only one way to start. And we build up the diagonals one at a time. The principle is that you stand on a spot and look back to see how many ways to get to where you are. That 6 is 3 plus 3. This is the pattern that we finished with. In particular, 1, 6, 15, 20, 15, 6, and 1. These are the coefficients that you get when you expand a plus b to the 6th. But that's not the only diagonal that's interesting. Every one of them has some property. Let's look at one near the top. This one, you see the numbers 1, 2, 1, which correspond to the coefficients that you recognize for a plus b squared. And that's true of every one of those diagonals. Well, this triangle has a lot of properties that are interesting, and they were developed and discovered by the French mathematician Blaise Pascal, who was working in the 1650s. He was interested in it particularly because he felt that he could get any power of a plus b simply by extending the triangle as far as you wished, at least in principle. Norman?
Well, that's all very well, but supposing you wanted, for example, to work out a plus b to the 20th, then you could do it, but it would be an awful lot of work because you'd have to set up a 20 by 20 grid and then do your calculation. What would be really nice is if we had some formula which we could use just to plug in values and then just calculate directly any number in this Pascal's triangle. Now, before we can get such a formula, what we've got to do is to describe this triangle symbolically. And the first thing is to set up some symbols to represent, to stand for these numbers. Now, supposing we wanted a symbol to stand for this number 20. First of all, we've got to locate its position in Pascal's triangle. And John's already pointed out that it's useful to regard this triangle by thinking of the numbers on diagonals as lumped together. So let's identify the diagonal of that number and then its position on the diagonal. Well, it's on the 1, 2, 3, 4, 5, 6th diagonal. And how far down? Well, count the b's. No b's, 1 b, 2 b's. Here we choose 3 b's. So 6th diagonal, 3rd down, 6, 3 are the pair of numbers which identify 20. And the symbol we use to stand for 20 in Pascal's triangle is 6C3, standing for 6, choose 3. What about this one? Well, that's in the 5th diagonal, but we're still choosing the same number of b's. So its position is 5, 3, and its symbol is 5C3. 5, choose 3. Sorry. Now, what about this one here? That's still on the 5th diagonal, but this time we're choosing 1b fewer, not 3, but 2. So the symbol for that is 5, choose 2. So that's a fairly effective way of representing any number in Pascal's triangle. And it would apply however big the triangle is. If you were in the nth diagonal and you were r down, then the symbol would be NCR, N choose R. And you could get triangles just like this anywhere. If you were in the diagonal 1 back, then you'd be n minus 1. And if you're on the same row, you'd be choosing R again, n minus 1 CR. On the same diagonal, but above there, you'd still be in an n minus 1 diagonal, but you'd be choosing not R, but R minus 1. So you can use those symbols to refer to any number in the triangle. What we've got to do now is to use those symbols to reflect the structure of the triangle. Now, how is this number obtained? It's obtained by adding those two. That plus that is that. And so that's the answer. How do we obtain this general NCR? Well, by adding n minus 1 CR and n minus 1 CR minus 1. Well, in the rest of this section, you'll have a chance to get used to using Pascal's triangle, and then you can use this symbolic representation to have a shot at getting a formula for any coefficient, any number in the triangle. So until next time, goodbye.